All right, guys, if we could all welcome Afif, please.
Thanks, guys. Thank you all for staying back this late. I am very excited to give this talk, so I'm glad you could all make it. The title of my talk today is Leveraging the Benefits of the Functional Paradigm. The part of the title I dropped is Leveraging the Benefits of the Functional Paradigm in Everyday Mundane Code. What I wish to cover today is, it is about functional paradigm. I would like, success would be for those of you who haven't done a lot of functional first programming for a while. How do we make this paradigm more accessible? The talk is not very academic. I'm not trying to dispel a lot of the complexities, define what monads are or otherwise. It's really more about, why does the paradigm exist? How can you, from where you are today, get value from it and walk away motivated to know more and to start your journey? I myself have been on this journey for almost more than 3 years now. I haven't started writing, for context, I haven't started writing like F# or anything in production. I dabble with Haskell frequently, and at work I look after about 28 developers with a lot of C# and how we can use functional to add a lot of value. So a lot of what I'm going to talk today is driving from those lessons. So the slide I have up here is working effectively with well, I was going to say legacy code, with code. The context we have today is we live in a world where we're writing far more code than any one of us can hold in our heads. And even if we manage that feat, well, the next 10 minutes when a check-in happens, that's out of date, or whatever is your release cadence. So we are more and more relying on being able to consume code that was already written, minutes, months, years ago sometimes, and being able to effectively reason with that code. Reason to the extent where we're trying to understand, why is it behaving the way it is. We're trying to add up a few things so that we can fix a bug or change some functionality. Or in some other cases, we're looking to actually extend the code, add some function on top. And what I have kind of stated out here is, what I feel works really well in this space is the ability to reason well. That helps with editing and asking questions. And the ability to extend via composition really helps when you have to add, so that you can walk away with confidence that in adding to that code, you haven't created a bug. But before we proceed, I think it's important to, what I want to do today is explore how the functional paradigm and the fundamental principles underpinning the functional paradigm can help us effectively reason well and effectively extend existing functionality via composition. But in order to do that, let's first kind of qualify that you and I think about reasoning well and composition the same way. Otherwise, you're on a different page. Let's start with the reasoning. What constitutes effective reasoning? Well, for starters, I feel it's not the same as readability. I got trumped on this a lot in the start when I had these conversations with my colleagues at work. Readability is very subjective. I'd often be in situations where I've done some refactoring and I shared with someone, and they kind of shared with the person next to them and go, does this make sense? And that person scratches their head and go, I can't tell heads for tails. And we go, see, this is not canonical code. This is not going to fly. What's happening there is, that's a valid response, but what's happening there is someone's responding to the fact that this is not familiar to me. I can't start navigating this. And hence it's very subjective. Reasoning, though, it's a different beast altogether. And let me start by throwing this into the mix. How effectively can you reason through this? Let's take it in for a moment. It looks a lot bad over here. It's not that bad, actually. For context, I come from this country. I've driven on these roads. I did not deliberately pick something that was monstrous. I have no problem navigating this. It's very intuitive and very subjective. But let's analyze it anyways. There's a bit of structure. Cars on the right, bikes on the left. Not everyone's following it. People are walking from the side, except not everyone's following it. Incoming, outgoing not everyone's following it. And then you've got, vehicles on the road, except you also have an animal. So I think the only thing constant with this slide is there's always an exception to everything, right? Heaps of surprises, structure but very loosely followed, and really open to interpretation, right? Let's flip this. Actually, before I proceed, who's comfortable to be in the car here? Anyone? Come on, brave. Yeah, cool. Have you guys driven before on these roads? No? I love it. I have a ball driving on these roads. Right, so let's flip this. How effectively can you reason for this? Hopefully this is a bit more closer to most of us, right? Again, this looks really big because it's, zoomed out view. Sitting in a car, this is not going to look this bad and complex. I wanted to capture the magnanimity of the structure and how it all just sings together. But really, imagine for someone who's learning driving, how accessible is this? I can tell you when I first got here, it took me a while before I could get on the road. So many rules, laws and, whatnot. People drive on autopilot. That's a good thing because they're not worrying about so many other things. Rhetorical question, if I may say, but I'm guessing a lot of us would be comfortable with this one, reasonably. No? I can tell you if I were to speak for my wife, which I can't confidently most of the time. She's new to driving, still very basic, the sort of type where she could hardly maintain a straight line. She's not going to have that much trouble here. Here, she would not get anywhere close. Why? Because the barrier to entry over here is really low. Really, there's one simple rule, and I've learned driving here, right? Keep your eyes open, and if you're going to hit in someone, brake. Right? It's really that simple. I actually just learned by sneaking my dad's car out, and that was it. No lessons. Whereas over here, well, it needs to be learned. But you're more effective here. You're in the car, the only thing you're reasoning about is what you have to do, and most of everything else takes care of itself. So, what does that tell us about effective reasoning? Well, for starters, the less you have to reason with, the better. It's a muscle that if you exercise more, it's not going to get stronger, it gets weaker. Effectively applying logical thinking is very important. As you could see in the latter slide, there's a lot of logic there, and the most important one of them all, a common language needs to be learned, and that's where effort is involved. The first slide, very little effort, jump on the road, every person for themselves. Second one, not as approachable, but put in enough effort, sit a few tests, be on the passenger seat enough, and, you get through it. So, funny one. It involves some effort. Let's remember those three. For the rest of the talk, I'm going to refer how the functional paradigm, the underpinning principles, help us in reasoning better using those three markers. Now let's get to composition. What's effective composition? This is a funny one. Again, it's not the same as coordination. And often it's referred to like that. That's most of the code we write. And the thing with coordination that I don't like is this whole order and execution needs to be followed in lockstep. Get anything wrong, you will know it. Most of us, I'm guessing here, have played some form of this game. How effectively can you compose? You've got the whole landscape, multiple ways of doing different things, and you have a choice, you have enough context. Reasonably well, I'm guessing. I'm sure, well, if I speak for myself, I have gotten this wrong far more number of times than I care to admit. You kind of open this up and you can go, how hard can that be? There's a bit of pattern here. The screws goes in holes. You start screwing them up, and before you know it, it was meant to be done only one way. And before you know, you've kind of screwed yourself quite literally into a position where you have to, it's expensive to come out of. Now, if anyone hasn't seen the correlation so far, this is more close to how our code looks. We look at it, we feel there's a bit of pattern there. It can't be so hard. I can see things. I'm on top of it. Unfortunately, there's no manual for the code we have. There is a way to get it right. It's in different people's heads, hopefully in someone's head. But we often go, no, it can't be that hard. I can figure a few things out, and then we have a lot of surprises. So we can't effectively compose. We can coordinate, and with more context, we have a better chance of getting things right, but we're very far from composition. What does that tell us about composition? Action is deferred to the last responsible moment. Usage is driven by the context of the consumer, and allows for multiple approaches to the same result. Maybe a bit controversial. And again, if you haven't seen the correlation, imperative code, low barrier to entry, get in, and then every person for themselves. You get it right. When you get it wrong, you know straight away. Functional code, right? A lot of guarantees, a lot of laws, not as easily accessible, needs to be learned. High amount of reasoning, high barrier to entry. Composition, again, we can't do this in our code, and this is very close to where we are. So this is, okay, so we understand something about effective composition. So with that in mind, let's look at what are the fundamental principles that underpin FP, how do they promote effective reasoning, how do they promote effective composition, and really, how does that look like in practice in a typed language? I won't be able to get very far with this because the language I'm using is C#. The idea really is, like I said, I'll give you some low-hanging fruit examples, and I'll try to unpack them to the fundamentals. Idea being, some of that you can implement today, but really you walk away with not being kind of scared with a lot of cryptic academic mumbo jumbo, and you're happy to navigate that yourself. It takes a while. Without further ado, these are the 3 fundamental principles that underpin this paradigm. For context, it's not that it's in the tweet, so I know, because I've been trying to get my head around this for 2-3 years. I myself also saw that, but then it was it was good to see that I wasn't imagining things. So total, they return an output for every input, deterministic and pure. The rest is just composition you can learn over time. Any surprises? Come on, tough audience. Immutability is not there, right? A lot of times when you say function programming, basics, whatnot, immutability pops up first, right? Recursion pops up a lot, right? It's not there, because all of that can be derived if you adhere to these. And the beauty of it, if you apply this lens, is you can, as you will see for the rest of the talk, you can kind of take this and apply to what we do today. If you don't get very far, because it does require learning a new vocabulary, as we saw under reasoning, where we kind of deduced it needs to be learned. At a minimum, I hope it will show you the gaps that we have today.
Doesn't purity imply immutability?
It does. Purity, purity does imply immutability. Now the talk is broken in these 3 sections. So if you have questions, you can choose. You can ask them then, or you can easily wait till I finish one section, and then you can call them out if you feel I haven't covered it already. Let's start with total functions. So total functions return an output for every input. How hard could that be? We'll find out. A function is a unit. In OOP, you could say, on a class you have an object, on an object you have a method. A method is cohesive, hence it's a unit. It takes in some input, it returns an output. Except that you see that when you pass it with, so in the first example you can see for 1, because it's strings, you give it some things, it passes, but because they are strings, you can give it whatever values you feel like. And if you do that, you get an exception. It blows. Now that is not specified in the contract. If you simply observe the contract, that does not tell you that while I allow you to give me strings and whatnot, only if they match my rules will I give you a custom, otherwise I'm just going to give you a lot of ugly exceptions. If you really had to reflect that in the contract, you'd have to basically go, I can give you a customer sometimes, on other occasions you're going to get a bunch of error messages. And you can figure out what you've done and adopt accordingly. Why is this important? It's so that when someone consumes this, they know it's a possibility that they can get things wrong, and they can use that feedback. I was being lazy, hence I used string. You can easily put a more stronger type in there. For non-visual representation, for looking at some code, this is how it normally looks like. The first step is where we have constructors, we take in the values. If everything is good, it's constructed. Otherwise, argument null exceptions, whatnot, other exceptions. I didn't write the whole code out. If you compare that to, at least what I'm advocating for today, is static. The constructor is private. You take everything in, you validate. If things don't go well, you collect them as errors. You return those errors. Otherwise, you return the customer. What's not obvious here is there's implicit casts which ensure that when you return the errors on line 84, the compiler knows you're returning a list of errors. It's expected a type of either, and then I'll just match that, which reminds me I haven't qualified what an either is. So we had a tuple here. The problem with the tuple of string and customer is while it tells you I have possible two return types, it doesn't tell you it's one or the other, right? To the untrained eye, they just go, okay, I'm getting a tuple which will have list of strings and a customer. When in reality, what they try to say is it's one or the other. The easiest way you do that in a typed language is you inherit that and you go, let me call it or you don't have to necessarily inherit that, it's not rocket science. You could just create a class called either, which has those two values on it, and you ensure that it can only be constructed with either the list of errors or the customer. And by virtue of calling it either, you give away that this type will either hold some errors or a result. And that's why you can see my return type here is an either, very simple class. And you return that, it'll be the compiler casts that into that, or you return the customer, the compiler casts it back into that. What we do here is anyone consuming this, without even having to read this method, they will understand that and accordingly adopt. Whereas on the first case, you have to read the method to understand that it can throw exceptions. Again, these are practices we have carried because, not so many years ago, probably code bases were not that big. We could afford to read a lot of lines of code. So what are we doing here? If you zoom out, and if you look at this as the domain of the application inside the green, and the red is the domain of the runtime, that's where you interact with values, raw values. You're kind of parsing those values in. They could be from another API, from an end user, and you're kind of giving some feedback to go, I accept the date time, but if it's not what I like, I'm going to give you some feedback around what's wrong with it, and then you can accommodate accordingly. And then eventually assuming that whoever is interacting is interested to get it right, they do come in, but once they do now come in, we have done all the validation. Hence, we now parse them into types that are the domain of the business. These are strongly typed, and hence they're no longer primitives. What does this do for us? It means that when these types get passed around in our domain, in our functions, we never again have to ask the question, that's a string. How do I know it's a valid postcode? Because that question was already answered when that was first parsed, and now it represents a type that already encapsulates that. It's a lot more cohesive. Imagine not having to write validation code. So now, where you had functions like that on the top, where you define by first name, last name, email, without looking at the implementation of that, you could easily imagine, well, even though its core domain is not to understand if that is valid or not, a sensible developer will try to do some form of defensive programming there to go, what if I'm given nulls? What if I'm given, a dot for an email address or whatnot? Is that the right behavior? And they try to accommodate for that, when really that is not the core responsibility of that function. But if it was the second, that's a lot more sane. Helps with improved reasoning. You never have to think about, is this the right value? That question was answered when those values were interpreted and they came in. So all these functions can now be a lot more safer. How has totality helped us here? When we started, we talked about totality and said it's about having an output for every input. Because we consider that principle, we narrow down the scope of all the inputs you want to handle, right? Because if you hadn't, then, because in the scenario over here, where you have to, well, then you have to account for it. Because you have accounted for it there, you can choose to narrow it over here, which means it makes life easy for a heap of all the code you write inside this space. So what have we learned so far from this principle? By removing input validation, that is not core to the domain of the function, we have made the function more cohesive, right? And a consumer better understands what are the preconditions to calling this function. If you do want to call it, you've got some strings, well, find a way to parse and construct them first, right? Not just put it in here. Let's take this a bit further and explore totality. So far, we have constrained our input types so that we don't have to handle and express a lot of behavior in our output types. That's taken care of. What else can happen? It's a find by method. What if it doesn't find a customer? What we do today is, well, you still get a customer, but it may be null. And that'll be up to you to, if you bother with that, to check with it, and otherwise it'll just blow in funny ways. Or if you really want to go defensive programming, then you just litter nulls everywhere, null checks everywhere. But the problem is even that doesn't solve the core issue, because even if you start checking for nulls, how do you know if the value is null? Is it because something went wrong, or is it because it's actually missing? Which one is it? It's hard to say. Well, we're in a typed language. Collections have always been around, and collections are where you can say it's empty or there's a bunch of values there. What if you had a collection where it could be empty or one value? We could use that, but then again, it wouldn't give away in the signature that the collection is meant to have 0 or 1 value. So instead what we do is we create a class that inherits from that collection and only allows for 2 constructors, which is a constructor that takes no value or a constructor that takes 1 value. And hence it's an optional. So now we can clearly understand this method and go, okay, it's going to look for a customer using these values. It may not find anything. You will need to handle for that case. What else what else is involved in totality here? What else have you missed by design? Exceptions. You see, we are calling across the network, and the network will throw exceptions, unfortunately, by design. And we know about this ahead of time, right? So, again, the onus is on us for totality, that we do express that and go, I may encounter an exception when trying to find a customer, right? And you will have to account for that. This is not defensive programming. This is because we are kind of indicating that I'm going to traverse whatever I'm going to traverse medium. By design, that medium can throw exceptions and I have no control over them. So you will have to account for that. So in this case, the either does not have errors because they're not domain. It's just an exception. You can type it if you want. Now, what I'm trying to do here is not propose reinventing exceptions or find a different way. What I'm simply calling out is exceptions, when they were first brought in, were proposed as a way of getting out of situations that you never anticipated, right? It's like when you write a flow chart and someone points a use case and goes, what if you go here? And you go, well, I didn't draw that line in my flow chart, right? It's a scenario you never anticipated would happen. And that's when you come into that scenario, you just blow up and the program stops and goes, I need more input from the person who has written this. They're not meant for situations where we know and we're just using them generously for control flow. Why do we do that? Well, part of it is familiarity. Part of it is generally just lack of vocabulary, right? And that's why, recall again in reasoning, we said it needs to be common language that needs to be learned. So once you understand that you can use things like eithers and that all exceptions are not actually exceptions, you can kind of bring more reasoning to your API. By API, I don't mean web API, I mean just application programming interface, like any method we write. So if you were to use this, now the types inform the consumer that finding a value is optional by design, The types inform the consumer that an exception is possible by design. Right? We have brought a whole lot of reasoning to this code because even without having to inspect and see what else can happen, the consumer is informed that they have to handle for these use cases. What gives of composition though? In the start, we had that method find by, and let's say there was another method called is preferred. And they perfectly line up because the find by returns you a customer and is preferred takes in a customer, so you can compose them. Call one, take the output, pass into the other, and you have your answer. Now, what we did along the way is we improvised and said, well, find by doesn't just give you a customer, it gives you a whole heap of other use cases too. Might give you an exception. If there's no exception, may or may not find a customer for you. What does that do for our composition here? Clearly, that above the line of code above is not going to compile. This is what normally follows. You'll have to rewrite the is preferred method so that it can take that value in. You have to manually unpack everything, right? You gotta go, well, if you have a result, then great. Oh, sorry, if you don't have a result, then you have an error. I'll return that. Nothing to add here. If you do, let's get the optional value out. If there is nothing in there, again, nothing to add here. Let's just return that. Otherwise, I'll call the method that was originally intended, that one, right? So you forced a downstream consumer to handle some of these concerns when they really have nothing to add. They're just basically walking through a few branches and going, I'm not going to do anything here. I'm only interested if you actually have a customer. Again, for completeness sake, implicit casts are kicking in, and that's the reason why either.error gets converted into the return type and optional.empty gets converted. All of the returns basically get converted. By the way, this code there's no guarantee that it compiles. I didn't write it in a IDE. There are a few things this will not completely compile, but I want to take away the trickery from the session right now, so 90% you get the message, for those who wanted to ask later. So what do? This is a rookie mistake. This is what you do first when you first start doing these things, and the first thing I found normally at work is people go, all my API is now littered with these return types. I'm forced to kind of travel with them everywhere. Every method has been rewritten to do this, because that's the only way to compose. Because there's not a lot of specificities in here except for that actual line, we can make it all generic. It's not very different. It's the exact copy-paste of the exact same code, remove the types to make them all generic, and the is preferred method has been passed in as a map. The reason why we can do that is because that code, like I said, does not have anything specific to the actual is preferred. It's literally saying, if there's no value, if there's an error, return that. If there's no value, well, return that. Otherwise, actually branch into the specific code. Once you have that, you can now leave the original is preferred method as is and still have your composition. So there are ways, right? So this is not writing more code, because these are branches that were always there in that code or in the behavior of the domain. You would always get a null, you could always get an exception. We just made it explicit. And then the cases that are not relevant to you, we captured that in some generic code so that they don't get proliferated in consumers that don't care about them. So that's the visual representation. F is your original function, find by. It's got 3 possible outcomes: an exception, an empty value, or the actual customer. G is our function that we're going to compose, which is the is preferred one. It only cares about one of the possible outcomes, not the other. But to compose, obviously, you'll need to handle all the 3. Hence, you kind of write this wrapper function that says, for these other 2, not concerned, I'll just pass them along if they don't qualify. But if it happens to be this, I will then call the actual function compose and then continue with the 3. Or if G happens to be a function that says, I'm also interested in an optional value, as in a missing case, because I have some business logic to operate on it, well, your pipe can be rewritten in a way that it doesn't walk all the way down here. It just walks till here and goes, the moment you have an optional value, I'll pass it down to my map. Some generic code goes a long way. The key thing I want to point here is one of the reasons we don't do this, one of the reasons we don't use eithers and whatnot, one is lack of vocabulary. But the other is probably the fact that we don't understand exceptions, when to use and when to not, which I hopefully have qualified. But really the main one is we just fear it will break composition. Because when you don't have this, it's nice and easy. The null case is not represented. The exception case is not represented. You can just continue writing code as if nothing happened. And that's where the problems start. So you can be explicit and yet not proliferate all these concerns all the way through. Explicit, yet transparent, right? So we started from find by. We said we first started by constraining the input domain, put types in it, so that we don't have to cater for the strings, and then we said we may have a missing, we may have an exception, and that's really all of that constitutes totality. How has this helped reasoning? By capturing all known behaviors within a type signature, it's made possible for the consumers to elect into what behavior they wish to build on, which is what we saw with the G. They can elect into what they want to build on. I only want one use cases, or I only want one use case, or I want both use cases, or maybe even three if you wanted. In which case, if you wanted all three, you don't need this thing. They just seamlessly compose. And then simply follow the types, and all known concerns are addressed. You can be explicit, because now what happens is when you write a function that says, I'm bad with names. What is the name of the function? Is preferred. Because is preferred function says, I only want a customer, and it can see the function above is giving it an either of an exception or an optional customer, you can be sure that whoever's written that has nominated themselves out of those use cases. It's not because they're not aware. They've explicitly seen it and gone, nope, I have nothing to add in those events. Only call me if you have a real customer. So it becomes a lot more easier now. That is totality. Any questions so far? It's a big elephant in the room I've cancelled. No more exceptions. Are we ready? Okay. The next one. Deterministic functions. They return the same output for the same input. Let's start with a nice and easy example. Enumerable values count. Let's say the values are A, B, C, and D, and I invoke it with a count of 2. I could get A and B. Let's say I invoke it again. Probably get A and B again. Who's up for the fact that I'll get A and B on both occasions? 2, 3, 4, 5. Okay. Or maybe I could invoke it once, I'll get A and B. And then if I invoke it again, I'll get C and D. Who's up for the fact that I'll get A, B, and then C and D? 1, 2. What's everyone else thinking? Sort of trick question. Okay, both of those cases are wrong. It is a trick question. I'll tell you why. I'll tell you why. It's an enumerable. If it was already invoked, if you're looking at this code and debugging through it, right, or you're looking to write a log, if that enumerable was already enumerated once, and now I ask it for the next top 2 values, what am I going to get? B and C. If it was already enumerated twice, and then I run this code, I'm going to get C and D. If it was never enumerated before, I will get A and B, and then when I call it again, I'll get C and D. So it's anything but deterministic. What's happening here is the enumerable is carrying some state with it, of the enumerator. Right? It's not completely transparent. Surprise. You need to know more than what meets the eye. Right? It's there for a reason. I'm not bagging enumerable. I'm just saying, when you have functions like these and you just take them at face value, you can have surprises. How would you fix it? I mean, without enough context, I can't comment how would I just fix this. If that enumerable is from the database, it's there for a reason. because it's only on demand enumerating and getting records back. But otherwise, if it's not required, you can just have it as an iRead-only collection or something. Let's take a completely different perspective. Get current weather reading at location. Let's say, I won't say Melbourne, Sydney. I call it once, I get the reading, 35 degrees, sunny. Let's say, I don't know how long I want to wait, 5 minutes. Long enough that the weather doesn't change, let's say. Or it does maybe subtly, I don't know. And I call it again. Will I get the same values? Of course not. Because there's some context there. Get current weather reading. Now if you want to remove that context for it to be made deterministic, you'd have to supply the time and go get current, get weather reading as of that time or for that time. So get me the weather in Sydney for midnight today, and it'll give me whatever is the weather. And if I call it again for the exact same values, whatever, sometime later, who's up for the fact that I'll get the exact same reading? Quite a few, majority? You're not right. Well, think about it. If you pulled out your app right now and checked let's say will it rain, let's make it more concrete. Will it rain in Sydney in 2 hours? Or Melbourne in 2 hours? And it said, no. 10 minutes later, if you pulled it out and said, will it rain in Melbourne in 2 hours? Well, if you know more information, then yes, it may have rain, it will. Because in 10 minutes you have gathered more information. So the missing context is reading as of. If the time right now was 8 p.m. and I ask that question, and 10 minutes later if I say, give me that reading as you knew it as of 8 p.m., well, that is more context, right? So again, missing context. Now who's up for the fact that with that, it's going to be deterministic? I'm scared you guys now. Well, the answer is without knowing more, I can't say if it is. What if it's calling a weather API in the back and who knows how that API is working? There's just not enough information there. If you give me a bit more information and say, well, we've already pre-computed all the values for the next 3-4 hours, so it's already saved in the database somewhere, and if you can pass me that list in here, well, then it's deterministic. Because now I know the list that I'm going to search for these values. But then what if that list is huge? And you just cannot do that, even if it's for the next 2 hours. What do you do then? How do you make this function deterministic? We've kind of gone, well, I'm happy to give you the weather reading, provided you fulfill a dependency I have on my environment. Which is, I need to kind of access a weather reader. Give me that weather reader, and I'll give you your weather reading. Now, in function programming, functions are values. So that's a value. Now, that value is not going to change. So that is safe to say that is deterministic. Call that 500 times, you will get the exact same value. Right? What is that weather reader? It's a delegate. I mean, in this case, it's a delegate. Weather query returns a list of weather reading records. So you can kind of now decipher and go, okay, probably this method is kind of internally using this, calling it, somehow taking those 3 variables, constructing a query, getting a list of reading records, and then, I don't know, doing something funky on that and creating a weather reading. Right? So what did we do here? We inverted the dependency chain. Instead of taking that in and making it and not making it transparent, we pushed it out to the consumer. Right? And that's the reason why it's static. The static keyword is what tells you this is all there is to it. Right? Now, why do we not do this? What gives? Again, composition. I have another method that I need to call. Calculate rain probability for that weather reading. How am I supposed to compose that? I want to call that method, give it a weather reading, not give it a func that takes in a weather reading, which is itself a func. Crazy. Well, Same deal. The same principles repeat over and over again.